Welcome to the Deep Dive, the show where we unearth the most fascinating insights from cutting-edge research, delivering you the essential knowledge you need without the jargon. Think about it for a moment. We're constantly surrounded by this invisible ocean of information. Countless conversations, massive data streams, critical commands are all flying through the air around us every single second. But how do our devices, the ones we rely on for everything, from calling someone to finding our way, how do they actually make sense of this chaotic, invisible world?
How do they pick out just one voice or one specific data packet from all that noise? Today, we're taking a deep dive into precisely that. We're going to explore something called automatic modulation classification.
Our mission today is really to pull out the most important insights from some groundbreaking recent research on a really advanced approach to AMC. We're going to be dissecting a fascinating new model. It's known as a dual-stream CNN-BiLSTM model with a tension layer.
Wow, okay, that's a mouthful.
It definitely is. But by the end of this deep dive, you'll understand why this particular architecture is such a significant leap forward. A leap in teaching machines to truly listen
to the radio spectrum will show you not just what it does, but crucially, why it matters so profoundly.
Right, and when we talk about why it matters, it's hard to overstate.
Spectrum they're operating in.
It's incredibly critical. You've hit the nail on the head. AMC is fundamentally the bedrock for all of that.
Exactly. And if we sort of connect this to the bigger picture, its importance really extends into areas you might not immediately think of, like military applications, for instance.
Okay.
In really congested electromagnetic spectrum, where countless signals are flying around, identifying and tracking specific signals. Well, it's absolutely crucial for things like electronic warfare and tactical operations.
And this is where blind modulation identification comes in. It's about operating without prior knowledge of the transmitted data or the channel characteristics.
So completely in the dark.
Pretty much. It's about being able to...
Okay, let's unpack this a bit more. You mentioned AMC is absolutely critical, but to someone maybe not as deep in this field, it might sound like something your smart devices should just do. What's the trickiest part about it? Where do conventional approaches really fall short?
Yeah, it's far from simple, and that's precisely because we're usually talking about blind modulation identification. What that means, fundamentally, is the receiver, the device, trying to figure out what kind of signal it's picking up,
often has absolutely zero prior knowledge about the data that was actually sent.
Right, none at all.
None. Think about it. It doesn't know the content of the transmission. And beyond that, it often doesn't know...
These are all parameters that would typically help a receiver lock onto and understand a signal. Without this information, well, it's like trying to understand a conversation where you don't know the language, you don't recognize the speaker's voice, and you don't even know the topic being discussed. It's that challenging. And then, you throw in the complexities of the real world. Radio channels aren't nice and static. They're dynamic. They're time varying.
They change constantly.
Exactly.
Yeah.
Signals can change their characteristics as they travel through the environment.
And you also have something called multipath fading.
Ah, yes, the echoes.
Precisely. That's when a signal doesn't just travel directly from the transmitter to your receiver.
Very jumbled. It's like trying to listen to someone speak in a crowded, echoing room where their voice is also being distorted and seems to arrive from multiple directions at once. It's messy. Now think about the implications for critical applications, particularly in military and security contexts. uncongested electromagnetic spectrum, communication engineers face this immense challenge. How do you ensure the safe and reliable delivery of your own vital communications, let's call them social signals, while simultaneously tracking,
recognizing, and potentially blocking hostile signals?
A huge balancing act.
It really is. This isn't just about, passive eavesdropping. It's about active electronic warfare. It means being able to instantly identify a potential threat, understand its nature, what languages it's speaking, and then take countermeasures, all in real time. This demands enhanced procedures for signal interception and processing that are, frankly, light years beyond what most commercial systems can handle. It's about maintaining information superiority in a really chaotic environment. And even, advanced commercial devices like
Software-defined radio, SDR, they still face these limitations.
Even SDRs.
Yeah. Typically, SDR systems rely on some form of supplementary information, maybe some side channel data, to adjust themselves.
just to manage the communication link.
Right, cutting down the chatter.
Exactly. In these challenging blind scenarios, minimizing overhead is key. Without good AMC, a receiver would essentially have to try every possible language or modulation scheme until it stumbled upon the right one.
Which would be incredibly slow and inefficient.
Terribly inefficient.
Yeah.
It's really the difference between just randomly guessing and truly understanding the signal environment.
So, okay, let's bring this back to us, the everyday users of wireless tech. Why should we care if our phones or Wi-Fi routers can
Quickly tell the difference between, say, BPSK and QAM64? It sounds like a highly technical problem deep in the weeds. How does it actually impact our experience directly?
Oh, it impacts.
Precisely. Imagine your Wi-Fi, your 5G connection, even just your Bluetooth headphones, working more seamlessly and reliably, especially in crowded places like airports or stadiums. AMC helps ensure that the spectrum, the shared resource, is used optimally. It allows more data to be transmitted effectively in the same amount of airtime.
which means faster downloads, smoother streaming, the stuff we notice.
Exactly. That's the user benefit of efficiency. Secondly, it's about adaptability. This kind of technology enables
Radios to adapt to different signal types completely on the fly without needing any human intervention.
So the device just figures it out itself.
Yes. Your phone, for instance,
which means fewer drop connections as you move around, potentially faster handovers between networks, and just generally more robust and reliable communication. It's about devices being smarter, more versatile, always trying to optimize for the best possible connection they can find. And finally, as we touched on earlier, it's absolutely crucial for security.
Right. The military angle, but also more broadly.
Definitely more broadly. In a world that's increasingly reliant on wireless, for everything from financial transactions to critical infrastructure control, being able to identify and
manage unknown or potentially malicious signals is paramount, whether it's defending against electronic attacks in a military context or simply ensuring the integrity and security.
Okay, it's clear that AMC is not just some niche academic thing. It's really fundamental to the future of wireless. And you mentioned earlier that the techniques for doing AMC have evolved quite dramatically over the years. We've gone from, traditional likelihood-based methods,
LB methods.
which basically compare a received signal against a library of known possibilities, and playtime-based methods, where engineers had to manually figure out distinguishing characteristics.
Exactly. Those required a lot of human expertise.
Expert features, they call them.
But more recently, the field has seen this massive shift towards machine learning and now specifically deep learning algorithms. That's really
convolutional methods you just mentioned.
They're just better at it.
They are. They can discern patterns and subtle characteristics in signals that are simply too complex or too minute for human engineers to explicitly define and code for. But perhaps even more significantly, the second reason is autonomous feature extraction. This is a real game changer.
Meaning the model figures out the important stuff itself.
Precisely. Historically, with those feature-based methods, human experts had to painstakingly engineer these expert features.
They had to sit down and decide, okay, this specific characteristic of the signal, maybe its peak to average power ratio, or its spectral shape, that's what we'll use to tell it apart.
And they figured out what features are important for classification entirely on their own.
That makes them much more flexible.
Far more flexible and robust. They can often adapt to variations in the signal or the channel conditions that they weren't explicitly programmed or designed for.
Okay, so deep learning is clearly the way forward. Now let's explore how it's tackled this challenge head-on. Before we dive into this specific new model, the dual-stream CNN-BiLSTM with attention layer, can you give us a quick tour? How has deep learning been applied to AMC so far? What kinds of neural networks have people tried? And what were their strengths and maybe
Their limitations that ultimately led researchers to develop this even more advanced approach.
Absolutely. Yeah, the field of deep learning for AMC has seen really rapid evolution. It's quite fascinating.
Exactly. Think of CNNs as being exceptionally good at identifying patterns in spatial data, just like how they excel at recognizing objects, faces, whatever, in images. In the context of signals, it's kind of analogous. They're great for extracting patterns within the signal's instantaneous structure, its immediate texture or shape at any given point in time. So early studies successfully applied CNNs to AMC, and they often outperform traditional methods quite handily.
but signals aren't static pictures.
Precisely the limitation.
While CNNs are excellent at spatial feature extraction, they're not inherently designed to handle the sequential, time-dependent nature of signals. The order and flow of information over time are
LSTMs are a type of recurrent neural network specifically designed to recognize patterns in sequences of data. They have these internal memory cells that allow them to remember information over potentially long periods. This makes them ideal for understanding time-related information in signals. Think of them like having a sophisticated short-term memory that can selectively recall important past information or forget irrelevant bits as the signal unfolds. So researchers started exploring LSTMs, sometimes adding them after CNN
to try and leverage both spatial and temporal information. And that naturally led to the progression towards hybrid models. These combine the strengths of both CNNs and LSTMs.
Getting the best of both worlds.
That's the idea. Trying to get the best of both. Use CNNs for extracting those immediate spatial features, what it looks like right now. And then use LSTMs for processing the temporal correlations and understanding how those features evolve over time, how it changes. The thinking is, a signal isn't just a static image, it's a dynamic sequence. You really need to understand both its immediate patterns and how those patterns evolve over time to truly identify it. More recently still, attention mechanisms have entered the scene, and the concept of attention is
Pretty much exactly what it sounds like.
Letting the network focus.
yes. It allows the neural network to pay attention to specific important parts of the input signal, rather than treating all parts equally. This is particularly useful for longer, more complex signals, where maybe certain segments contain much more discriminative information than others. An attention layer can dynamically learn to weigh different parts of the signal, essentially focusing the model's resources on the most relevant information. It's like telling the network, hey, this part is really important, focus here. So you can see this clear progression,
Right. From CNNs for spatial, to LSTMs for temporal, to hybrids combining them, and now adding attention for focus. Each of these architectural advancements built upon the previous ones.
deep dive today focuses on this truly advanced architecture, a dual-stream CNN-BiLSTM model with an attention layer. It definitely sounds like they're taking the best of what's come before and weaving it together into something even more sophisticated. Let's break down each part. Why is this combination so powerful? Let's start with the CNN part again.
Right, let's do that. Think of it like building a highly specialized, multifaceted sensor system, where each part contributes to a deeper understanding.
Right.
So, first core component.
The power of CNN, the convolutional neural network. As we mentioned, CNNs are exceptional at spatial feature extraction. For a radio signal, it's about identifying specific patterns within the
These detected patterns are then passed through a special nonlinear function in this case, something called ReLU, which allows the model to learn more complex relationships, not just simple linear ones. And importantly, they use a technique called zero padding. This basically adds zeros around the edges of the signal data before convolution, which helps it maintain a signal's structural form and prevents important information from being lost at the edges during processing.
So you don't lose the edges.
Correct. This whole convolutional process essentially
extracts a rich, detailed fingerprint of the signal's instantaneous patterns.
Okay, so the CNN spots the immediate patterns. Then the BiLSTM comes in to understand how those...
Perfectly put. Following the CNN, we have the intelligence of BiLSTM, the bidirectional long-short-term memory network. If the CNN is about the spatial what, the BiLSTM is all about the temporal how, understanding the sequence and time-related information. And the bidirectional part here is really key. It means the network processes the sequence of features from the CNN both forwards and backwards in time.
Both ways. Why?
Because looking both ways allows it to consider both past and future context when interpreting a particular
signal segment. This helps it perform much better signal entity recognition. It does this by learning these sophisticated internal gate weights. These gates allow the BiLSTM to select
yeah. It's much like how your brain filters out background noise to focus on a conversation, but also uses context to anticipate what someone might say next. This unique memory and contextual capability is what makes LSTMs, and especially BiLSTMs, so effective for understanding the dynamic, unfolding nature of signal data. Now, for what the researchers sort of hinted at as the secret sauce, the attention layer, this component is added after the BiLSTM layer.
So it looks at the output of the BiLSTM.
Exactly. It takes the temporally
aware features from the BiLSTM and then refines them. And this is what significantly boosts the model's overall accuracy. Imagine you're trying to read a very long, complex document.
That's basically what the attention layer does for the signal features processed by the BiLSTM. It allows the model to pay attention to specific important parts of that process sequence rather than treating all parts equally. This focused recognition is incredibly powerful, especially when dealing with lengthy data sequences, because it helps the model to better handle and recall critical information for those long sequences, ultimately identifying the most discriminative features for classification.
Okay, CNN for spatial, BiLSTM for temporal
context, attention for focus. But you mentioned this dual stream thing. That sounds like the really novel part here.
It is. It's a major strength and a key innovation, the dual stream advantage.
Stream 1 takes the IQ, in-phase, and quadrature vector. These are the raw complex samples of the radio signal, represented by their in-phase I and quadrature Q components. This is the fundamental direct representation of the signal's oscillations. It's pure form, if you will. Stream 2 takes the AP, amplitude, and phase vector. This is derived from the IQ components through standard mathematical transformations. It essentially translates those raw signal oscillations into the signal strength, or amplitude A,
and its precise timing relationship, or phase P.
So one stream sees the raw signal, the other sees its magnitude and angle, basically.
That's a great way to think about it.
Yeah.
Why?
Each lens IQ and AP reveals different aspects of the signal. When you combine those perspectives, you get a much more complete and nuanced picture than either view could provide alone. The structure of both streams, by the way, is similar. Each has its own CNN, its own BiLSTM, and its own attention layer tailored to its specific input type.
Okay, and you mentioned preventing overfitting.
Right, to prevent overfitting, which again is when a model gets too good at the training data but fails on new data, they use a technique called dropout.
This is applied within both streams. It essentially randomly turns off a certain percentage of neurons during each training iteration.
Sounds counterintuitive. Why turn things off?
It forces the network to learn more robust and redundant features. It can't rely too heavily on any single neuron or pathway, so it learns representations that generalize better to new, unseen signals. It makes the model more resilient. Okay, so now let's talk about how the streams come together. We have these two streams, IQ and AP, each processing the signal and ending with an attention layer that outputs a refined feature vector summarizing what that stream learned. How do we combine these?
They use a method called an outer product. This is a specific mathematical operation that takes the feature vector from stream 1 IQ and the feature vector from stream 2 AP and combines
more. It creates this higher dimensional representation that captures the combined insights. This outer product results in a sort of grid or matrix of combined features. This combined feature matrix is then flattened out into a single very long feature vector. This then just prepares the data for the final decision-making layer. Exactly. This blend vector, containing all the merged characteristics learned from both streams, is then fed into the final layer, a dense and softmax layer. This is where the model converts all those gathered characteristics into a probability distribution across each of the target modulation schemes. It essentially gives you a confidence score. I'm 98% sure this is QPSK, 1% sure it's BPSK, 1% sure it's something else, and so on. The highest probability wins. And finally, just quickly on the optimization and training process, how does the model actually
learn? Well, to guide the learning, they use a cross-entropy loss function. Think of this as a very precise scorecard. It measures exactly how far off the model's probability predictions are.
Atom is a very popular choice in deep learning. Why? Because it's generally fast, computationally efficient, and requires fewer manual tuning settings like the learning rate compared to some older optimizers. It's like a smart learning rate adjuster, adapting how much the parameters change based on how the training is progressing. It helps the model learn quickly and stably without getting stuck. The training process itself is iterative, just like a student studying. First, all the model's internal parameters, the weights in the CNN, BiLSTM, etc., are randomly initialized. Then, the huge
training data set is randomly shuffled and divided into smaller chunks called mini-batches. The model processes one mini-batch at a time. It takes the raw signal samples, converts
exactly, and then uses the atom optimizer to update its internal parameters via a process called backpropagation, essentially nudging the parameters in a direction that should reduce the error next time. This whole cycle process of batch, calculate error, update parameters is repeated for all the batches in the dataset. That's one epoch. And this is done for many epochs, maybe 100 times in this case, until the model's performance on a separate validation set stops improving, indicating it has learned as much as it can without starting to overfit. Then it's ready.
So essentially it's taking these multiple perspectives of the same signal as raw components and its amplitude phase characteristics, feeding them through parallel streams that use CNNs for spatial patterns, BiLSTMs for temporal sequences, and attention to focus. And intelligently merging the insights before making a final classification. It's like a super-powered multi-sensory listener designed specifically for radio signals. That's really impressive. Now, okay, this all sounds incredibly sophisticated on paper, but how did they actually test it? What kind of data did they
Wet it to prove its effectiveness, especially against, real-world messiness?
Right, that's absolutely the crucial question. Theory is one thing, practice is another. The researchers put this model through a very rigorous
Using a standard public benchmark data set like this is really important for reproducibility and fair comparison. It means other researchers can test their own models on the same data and see how they stack up. It's a common standard in the field. And let me give you some details on this data set because it's key to understanding the results. It's absolutely massive. It contains 1.2 million examples of radio signals.
Wow, 1.2 million.
Yeah, and for each of the modulation types included, and at each different signal-to-noise ratio, SNR, which we'll talk about later.
6,000 distinct examples. Every single example provides the signal as its in-phase ion-bolt concerture components over a sequence of time steps. These
exactly. Extremely noisy, a signal almost buried, all the way up to a very clear plus 18 dBs. And it steps through this range in increments of 2 dB. This wide range of SNR levels is absolutely vital because real-world signals arrive at a receiver with vastly different levels of noise and interference. You need to know if your model works just in clean conditions or if it can handle the messy reality too. And what makes this RML 2016.1 LRB dataset particularly valuable and why it's such a good test is that it simulates
real-time radio communication conditions by incorporating various realistic error effects.
Ah, so it's not just clean, perfect signals plus noise.
Not at all. This isn't just clean theory.
Meaning the signal's frequency and timing are perfectly stable, they drift slightly over time, just like they would in real electronic devices due to imperfections or temperature changes. It also accounts for time-varying multipath fading of the channel impulse response. This simulates how signals bounce off buildings, reflect, interfere, and distort in complex urban or natural environments, and how those paths change over time.
The echoes we talked about.
Precisely. And how those echoes change. And of course it includes additive white
Gaussian noise, or AWGN, which is that sort of ever-present background static that degrades all wireless signals to some extent. All of these combined factors make the testing conditions very, very
on the 7 digital modulation schemes that are most relevant for next-generation wireless communication systems.
The workhorses of modern tech.
Exactly. These are things like APSK, CPFSK, PFSK, QAM64, QPSK, BPSK, and QAM16. They chose these because they're fundamental to things like Wi-Fi, cellular communication, satellite links, and so on. Each signal example in the dataset has a specific link, 128 time samples, and is represented by its 2 components, I and Q. So it's like a 2x128 data snippet for each example. Okay, so for the actual training and testing details, they took this massive dataset and logically split it.
A large majority, 80% of it, was used purely for training the model. That amounted to around 768,000 unique signal samples. The remaining 20%, about 192,000 samples,
absolutely crucial. This clear separation ensures that you're evaluating the model's ability to generalize to data it has never encountered before, giving a true indication of its real-world potential. They also carefully set the hyperparameters and knobs you tune during training. They decided on 100 APOCs, meaning 100 full passes through that entire training dataset. They used a batch size of 1024, processing 144 samples at once during each training step. And the atom optimizer, as we mentioned, was used with a specific learning rate of 0.001.
It's worth noting, all this heavy lifting, training on nearly 800,000 samples for 100 epochs. It required significant computational power. They used a specific high-end NVIDIA
Definitely not for the training phase, no. And the model itself was implemented using popular standard deep learning libraries. Keras running on top of TensorFlow. So this whole rigorous setup, from choosing a realistic, challenging, open-source data set to the careful division of training and testing data and the clear specification of hyperparameters and hardware, is all designed to ensure a fair, comprehensive, and importantly, reproducible evaluation of the model's performance against the complex challenges posed by real-world
radio signals.
Okay, so the stage is set, the sophisticated model is built, the challenging, realistic data is ready. That sounds like a very robust testing environment. Let's get to the results.
It absolutely did, yeah. And the results are really quite compelling, especially when you compare them to previous work. Let's start by looking at the accuracy fluctuation with APOC during training. One of the major concerns with complex deep learning models, as we touched on, is overfitting. That's where a model basically memorizes the training data perfectly, but then fails miserably when it sees new, unseen data.
It doesn't generalize.
Exactly. But the proposed model, very encouragingly, does not exhibit significant overfitting. If you look at the graphs they provided, you can see that both the accuracy on the training data and the accuracy on the separate validation data, a small part of the training set held back during training to check progress, rise together steadily. And importantly, they both reach a plateau or saturation point around 80 epochs. This indicates that the model is learning efficiently from the training data, but is also generalizing well the data it hasn't explicitly trained on.
That's a critical characteristic for any practical deployable model. Now, for the real test, accuracy versus SNR, how well does it perform across different noise?
Moderately clear to very clear conditions, its accuracy jumps to over 96%.
Wow, 96%, that's almost perfect identification.
It's incredibly high accuracy, pushing the boundaries of what is achievable, especially considering the complexity of the 7 digital modulation types it's distinguishing between in the presence of all those simulated channel impairments. But the truly significant finding here, the real validation, is its comparison with existing models. This is key. The researchers didn't just test their model in isolation. They took several other contemporary high-performing deep learning models for AMC from recent literature models like a standard
CNN-BiLSTM, a CLDNN, other CNN variants, and they trained and tested them under the exact same conditions. Same data set, same training parameters, same data split. A fair...
Exactly. And the proposed BiLSTM model performs superior to all of them across the board. This isn't just, a tiny 0.1% improvement. It's a measurable and statistically significant leap in performance compared to these established architectures. And just for context, prior research, like the paper introducing that CNN-BiLSTM model they compared against, had already shown that that model significantly outperformed traditional non-deep learning machine learning techniques, things like k-nearest neighbors, linear support vector machines, random forest classifiers.
Okay, so this new model is beating the model that already beat the older methods.
Precisely. So by outperforming even that high-performing CNN-BiLSTM model, this new dual-stream architecture indirectly demonstrates its vast superiority over those older, less sophisticated feature-based or statistical methods. The paper notes that the classification accuracy of the proposed model is noticeably more significant than the reference models across a really wide SNR region, from 16 dB all the way up to plus 20 dB, proving its robustness not just at high SNR but across the spectrum. To get an even deeper, more granular understanding of how it's
performing, the researchers also provided the confusion matrix.
The matrix that shows where it gets confused.
Exactly. A confusion matrix is a fantastic visualization tool. It's basically a grid where the rows represent the true modulation type of the signal, and the columns represent the type the model predicted. The diagonal cells show the percentage of times it got the classification correct, true positive rate. The off-diagonal cells show where it made mistakes, for instance, how often it mistook a QPSK signal for a BPSK signal, or a QAM16 for a QAM64. It gives you a really detailed picture of the model's strengths and weaknesses for each
specific modulation type. And they broke this down by looking at the confusion matrix at different SNR levels, which is very insightful. Looking first at low SNR, specifically 86 dB. Remember,
it's highly impressive. Given the challenge, it means that even in conditions where the signal is heavily corrupted, the model can still make an educated guess that's correct more often than not. You can see some confusion, particularly between similar schemes like QAM16 and QAM64, which is expected in high noise, but it's still performing remarkably well. Now step up to mid-range SNR, say 0 dB. Here the paper notes
close to 1, or 100%. This indicates that the model can adequately identify most of the modulation schemes quite reliably in these more moderate noise conditions. The confusion between
Okay, the takeaway seems to be not only is it incredibly accurate, especially compared to previous models, but it's also impressively consistent across a wide range of signal conditions. It degrades gracefully in heavy noise, but becomes near perfect when the signal is clear. That's a huge step forward for real-world reliability. But, and this is often the catch, how does it stack up in terms of practical considerations? Things like complexity and speed. Accuracy is fantastic, but if it takes, I don't know, a week to train or requires a dedicated supercomputer cluster
Just to run in real time, that really limits its practical utility, doesn't it?
You hit on arguably the most compelling comparison in the paper, and this is where the proposed model truly differentiates itself and becomes highly practical for real-world deployment. They did a direct comparison, focusing on complexity and time against one of those high-performing contemporary architectures they use as a baseline. Let's look at the specific numbers they reported, because they're quite striking. First, let's talk trainable parameters. This is basically a measure of the model's complexity. You can think of it as how many adjustable knobs or weights the model has
internally that need to be learned during training.
More parameters generally means more complex, harder to train.
Generally, yes. More parameters often means more potential.
It's a huge difference, a massive reduction in complexity. Fewer parameters mean significantly less memory consumption, which is critical for deploying on devices with limited resources like embedded systems or mobile phones. It also often translates to faster operations, both in training and inference. It makes the model much more lightweight and potentially easier to implement in hardware. Okay, so it's much simpler. But do they sacrifice accuracy for that simplicity? Well, let's look at the overall accuracy again. The proposed model, with its 145K parameters, achieves that 68.23%
average accuracy across all SNRs. The comparison model, with its 1.1 million parameters, achieves 64.5%.
Wait, so the simpler model is more accurate?
Yes, that's the really impressive part. It's not just smaller, it's apparently smarter, or at least more efficient in how it uses its parameters. It achieves measurably higher accuracy despite having dramatically lower complexity. This suggests the dual-stream architecture with attention is a very effective design, learning to be more precise with fewer resources. Now consider the training time. How long does it actually take to teach the model in that big data set using the specified GPU? The proposed model takes only 59 minutes to train for the full 100 epochs. The comparison model,
A staggering 219 minutes.
That's almost 4 times faster, from nearly 4 hours down to under 1 hour.
exactly. This is a massive reduction. For researchers and engineers developing these systems, this means significantly faster development cycles. You can try out new ideas, tune hyperparameters, and iterate on model designs much more quickly. It really accelerates progress in the field. Imagine how much faster you could develop and deploy new wireless systems or features with this kind of training efficiency. And perhaps most crucial for many real-time applications, let's look at the testing time, or inference time. This is how quickly the model can classify
A new incoming signal once it's already been trained and deployed. The proposed model classifies the test dataset in mere 2.9 seconds. The comparison model takes 8 seconds to classify.
Yes. For applications like dynamic spectrum accessing, cognitive radio, or adaptive modulation that needs to react instantly to changing conditions, or especially in electronic warfare, where milliseconds can literally be the difference between success and failure, this reduction in classification time is a potential game changer. It means signals can be identified and acted upon almost immediately, enabling much faster responses and more agile communication or countermeasure systems. So to bring this all together, to make the big picture.
The research strongly suggests that the proposed dual-stream CNN-BiLSTM model with attention layer achieves superior classification accuracy, as we saw demonstrated across the wide SNR ranges.
High accuracy, robustness, low complexity, and speed makes it an incredibly powerful and highly practical solution, well suited for real-world deployment in a wide array of future wireless communication technologies, from your next-generation smartphone all the way to critical national security systems.
So what does this all mean? We've taken a really deep dive into this dual-stream CNN-BiLSTM model with a tension layer, and it's absolutely clear this isn't just another small incremental improvement. This feels like a genuinely significant step forward in how we empower intelligent receivers, intelligent devices, to actually understand that invisible world of radio signals swirling around us.
Exactly. I think the research highlights several really key takeaways and implications for the future. Firstly, it powerfully demonstrates the remarkable effectiveness of intelligently combining these different neural network components. Using CNNs for their strength and learning spatial features, those immediate patterns within a signal, and pairing them with BiLSTMs for their superior temporal correlation capabilities, allowing them to understand the sequence, the flow of information over time. This hybrid approach really seems key to capturing a comprehensive understanding of complex
signal characteristics. Secondly, the crucial role of the attention layer is undeniable. It acts as that selective filter, allowing the model to dynamically focus on the most important
and its specific strength in classifying these modern digital modulation techniques is vital. The use of both the raw IQ signal data and the derived amplitude phase information processed through that unique dual-stream architecture. It just gives the model a richer, more diverse set of features to learn from, directly leading to its impressive accuracy gains. And finally, as we just discussed, the practical advantages are immense. That dramatic reduction in complexity and computing time, both for training and testing. This means this isn't just a theoretical breakthrough
confined to the lab. It's a genuinely deployable solution, highly suitable for real-life applications where speed, efficiency, and resource constraints are paramount. It pushes us much closer to
This technology isn't just theoretical. It clearly has direct implications for how our future wireless world is going to operate. From potentially faster, more reliable communication in our everyday gadgets, to enabling more sophisticated cognitive radio systems that can intelligently manage our increasingly crowded airwaves, and even potentially securing critical military operations by allowing faster identification of unknown signals. It really is about teaching machines to hear and understand radio signals in ways we previously couldn't even imagine.
And this really raises an important, maybe even provocative final thought for you to consider. As these AI models, like the one we discussed today, become increasingly adept at understanding and classifying even the most subtle characteristics of radio signals, what new frontiers does this open up? What new possibilities emerge from managing the ever-growing complexity of our electromagnetic spectrum? How might this lead to wireless systems that are not just faster and more efficient, but truly aware of their environment? Systems capable of making
instantaneous, autonomous decisions about how to best use the airwaves around them, perhaps cooperating or avoiding interference in ways currently impossible. And perhaps on a more cautionary note,
those are indeed fascinating and incredibly important questions for all of us to consider as these powerful technologies continue to advance at such a rapid pace. We definitely encourage you, our listeners, to perhaps explore more about cognitive radio or the fascinating intersection of deep learning and wireless communications. It's a field that's clearly evolving very quickly. Thank you for joining us